Hello YouTube viewers, welcome to my channel Science to Technology. In today's show, Rocket Monday, we're going to talk about ISRO's SCE-200 engine. So let's dive deep into it. Now this puppy is semi-cryogenic engine 200, as in 200-ton class. Now it's a heavy lift engine. Now which rocket is going to be used in, that's a different thing, because this is like build the engine. According to our needs, we're going to upgrade our previous rocket or design a new rocket. So first we have to have a big ass engine. So this is what it is, and this has 180 bar chamber pressure, and this can give you around 200 tons roughly, or if you want to be more precise, 230 kilonewtons in vacuum and 100 basically 1820 kilonewtons at sea level. So around that 200-ton class range. Now the specific impulse is around 335 seconds in vacuum and 299 in sea level. Now that's not a problem of engine, that's a problem of kerosene, as in like heavy hydrocarbon. We want lightweight elements going super fast or heavyweight element going hyper fast. Unfortunately, we cannot send kerosene hyper fast yet. So we kind of limited. So the only way you can get higher specific impulse is move up to basically methane, where you have more hydrogen, or you can go to ultra high lightweight speed, which is hydrogen. So in hydrogen, you're going to get very high specific impulse. Now, what does it mean? Like this specification, what does it mean? Like how does it stand against others? Basically, SpaceX Raptor 1, basically the first variant they built, that was 185. The Raptor 2 that they have built is around 225. And there is a very good chance they will not increase the power anymore. They will increase the usability, ease of manufacturing, those vectors, rather than increasing the power. So that's in the same ballpark. Then we have Blue Engine 4, this puppy, which will be used in Vulcan very soon. This is around 250 tons. So it's a bit more oomfish, because it was inherently designed in such a way where it's like they're gonna build a big ass rocket, but they're gonna have a few engines, much less engines compared to Starship, so to say. So that's their philosophy. So that's why each engine itself is a bit more powerful. 250 ton. And then we have the closest I could think of it is RS-25, that is 183 ton at sea level. At vacuum, it had much higher efficiency, simply because, again, hydrogen. So this is the whole context that ISRO is working at. So what was the design? Now be very mindful. It's not like I can directly go inside ISRO and ask, hey, can you give me the blueprint or how the heck it works or schematic breakdown. So this is the best estimate that I could do with all my limited knowledge. So you have to be relaxed a bit about that. So this puppy is stage combustion cycle. What does that mean? That simply means it has fuel-rich pre-burner and no unburnt exhaust. What does that mean? That simply means if you have ever looked at Merlin engine, basically Falcon 9 class rockets, you will see there is a big ass nozzle. Awesome. But there is also a tiny nozzle, and that's very black. The output coming out of it is very black. What is that? That's pre-burner exhaust. Now, pre-burner exhaust is a thing. Now, to design your rocket in such a way that pre-burner exhaust directly goes into the main chamber and does not get wasted, it adds extra layer of complexity. Now, it is desirable to do because it improves your efficiency. Per ton of propellant you are carrying, you can get more work done if you are more efficient. So it's desirable. That's why Raptor has it, but Merlin does not. And it's a more difficult thing to do, to have a closed loop system, so to say. So this puppy has closed loop system and fuel rich pre-burner, basically where you are charging everything, it's fuel rich. Now it's using a different kind of kerosene variant. Basically you take kerosene, you filter that puppy up, you filter a lot, then it becomes JP1, jet propellant 1. You filter it even more, like exponentially more, then it becomes RP1. However, what ISRO is using is ISRO Sen. Please do not ask me who named this. ISROSENE. I have no idea. ISROCene, basically kerosene, ISROCene, I have no idea. ISROCene is basically somewhere in between basically JP1 and RP1. So it's a bit cheaper. Basically, they are not removing sulfur as much as they need to, like all other rocket engine design needs to. It all has pros and cons, but if you are using a single use rocket engine, it does not make that much sense. It's almost like how other companies are using just a natural gas to power their system rather than using CH4. If you are using liquid methane, it's a bit more expensive. You are gonna get almost 90% of it in using basically liquid natural gas. So just use liquid natural gas. Not 90%, I say like 98%. So it is cheaper, basically RP1 and normal liquid oxygen at minus 138 degrees Celsius. Now this puppy has 3 turbo pumps or pumps, so to say. So 1, 2, 3. Now yes, this is huge. Yes, those are people fit. These things are huge. The engine is huge. So let's give some power context here. So oxidizer booster pump, basically pre-pump, so to say, booster pump is around 735 kilowatt. So not too much power. and it's running at around 7,000 RPM and it's around 77 kilos. So that's lightweight in terms of rocket. Then we come to fuel booster pump. That is even lower power, as in like 160 kilowatt of power, and that puppy is running at 7,100 RPM and weight is around 25.2 0.5 kilogram. Very lightweight puppy. Then we have the main booster, the main turbo pump. Now this puppy is the big daddy. That is around 35.7 megawatt. That's some serious power. And then it has speed of 19,000 RPM and weight of around almost half ton. So yeah, that's the main daddy. These two are just there to help this daddy. So let's follow the flow line, so to say. So we start with fuel. Now fuel gets to this puppy, basically low pressure fuel booster, so to say. Now here's the how the heck that fuel booster works. It took me a lot of research, but apparently it's using hydraulically driven fuel pumps. So it doesn't make sense. The power requirement is not too high. So it has hydraulically driven fuel pump. Then the fuel comes here to the main booster. Then you have oxidizer line. Oxidizer line goes to the pump, but because the power requirement is higher, it's using basically bypass of gas generator output, so to say. And then that's how it's being driven. So it also comes to the basically main fuel pressurizer. So now you have taken care of all the little pumps. Now the big pump, which is a single axle unit, almost like how BE5 is, BE4 I think, yeah, BE4 is single axle. So then you send all the data, pressurized oxygen and pressurized basically fuel into the gas generator. Here you burn it. Now of course you design your burn in such a way that it does not become too high temperature, because it will poof the turbine blade, so to say. So you make sure the best you can do without increasing temperature too much, but do increase the flow as much as possible. And from this, you will have a hot gas manifold. What does that mean? There is no liquid in this pipe. So what is going to the chamber, it's a fully gas, exactly like how Raptor is. Most engines, if they really want to be high efficiency, they try to achieve this, where you have complete gas going to the basically the combustion chamber. You really do not want liquid, or you want as little as possible. Main thing, you always want to send gas. And doing that with kerosene, that's a big bold move, but they are getting there. Now here's the that creates an issue. Is like, how the heck you're going to cool the chamber? So you take a basically bypass duct, so to say, from fuel pressurized fuel. You take it, you run it around the engine, you cool the engine, and then you ignite it here also, the remainder. So because be mindful, gas generator gets majority of your work done, but you still have to add some here. So otherwise this turbine has to become too high expense, basically too high cost, so to say. And this oxidizer low pressure pump driven system, it's too hot here. So there is a shiny tank of this size, so to say, that is a heat exchanger. That's dumping the heat down, so this turbine does not go poof. That's the whole idea. So you take oxygen, you turbocharge it, then you supercharge it, and then main burn it, and then you take basically fuel turbocharges, goes to the basically two main places. Main place number one, gas generator, runs the chemical cycle, then it goes to the basically engine nozzle, cools the engine system, then remainder goes to that system. Now what is the ratio? That part I could not find out. So this is the design of this puppy. Now, what about the development? Basically, this is a new design. India is trying to develop it. So India needed to build tools. Even if somebody gives you blueprint, does not mean you can just like, oh, I have blueprint, Control C, Control V. You can make things. You have to develop a lot of what we call jigs, tools, ecosystem. So all those things India built to make sure that ISRO can do this job. So one of my personal favorite, be mindful, this is a huge list if I actually wanted to explain everything. But like, these are the few things that I liked. Copper steel vacuum brazing. So especially for this heat exchanger, which is going to take care of the hot exhaust from basically gas generator going to the oxygen pre-booster, it needs lot of micro surface area. Basically you need two tubes, and the tubes have to have as lightweight as possible while having as much surface area as possible. So how the heck you have that kind of surface area? You etch it, but problem is how the heck you etch inside something? You can't. So what they decided is like have two sleeves, so to say. Sleeve number one would be copper side. That sleeve will be the main thing that is cooling. Okay, that's awesome. Here's the deal. How the heck you contain that? If you micro etch it, how do you seal around it? Well, somebody came up with a very interesting idea. It's like you take steel side. Now be mindful, this sort of thing has been done other times also, but now India can do this indigenously. We do not have to ask anyone. We do not need special basically memorandum of understanding or signed of certificate. So it's like, bro, we got this. We know how to do this. So you have steel, you have copper. Steel would be the outer sheath, and copper side is the main part that is trying to cool the gas. So on top of that, you basically deposit copper, 25 micrometer kind of. Now copper deposit, copper bonds very easily to copper, so it's Awesome, you did it. Now on top of that, you deposit silver. Silver also meets with copper very easily, but it also melts at lower temperatures. So that's a desirable. Basically, it will be your solder layer. So this is these three things: copper coating, silver coating. This is your one side. Steel. Now steel, if you directly try to make it marry copper, it's gonna get divorced very soon. So you have to put a mediator there. So that mediator is nickel coating. That is 5 micron thick. Then on top of that, you put copper coating. So this 5 micron thick layer makes sure that steel does not get divorced by copper. Now on top of that, now you put silver coating again. Now you put all of the sleeve together, and then you pull a vacuum from the inside. Basically inside this sleeve, you pull vacuum. From outside, you pressurize that puppy with argon, and then you heat it. And this silver basically solders away, and voila, you have very micro, basically a lot of micro channel, lot of surface area, and very good cooling capacity with very little mass, so to say, very little weight, so to say. So really, really ingenious design. And to be mindful, this is exactly how modern rocket engine nozzles are built. Of course, this ratio could change, the system could change, but logic remains more or less the same. So that's the whole point. Then we have a lot of development of high grade 3D printing system from Wipro Corporation. They are building basically assemblies for turbopumps, basically the fancy things. They are building that. They are using titanium 3D printers to get that done. That's an Indian company taking care of the situation. Then we had a oops moment, that was like Russia and Ukraine started a war. Basically, Russia started a war and Ukraine basically hold it off surprisingly well for surprisingly long. But that created an issue. We were thinking that we're going to build the engine and then we're going to send it there for testing. Russia has a lot of system, or send it to Ukraine for system integration and testing and all that. Just, but that went poof when Putin went poof. So at that point in time, that created a scenario where we did not have a world-class facility to test these things. We can build big ass engine, we could not test it. So we built our own testing ground. Because that funding was cleared, bam, we got all that clearance done, all the funding done, large test site was built. Now, where this engine will be used, the first customer of this engine is GSLV Mark III. If everything goes according to the plan, it should get like some seriously powerful engines, and hopefully the booster stage could become powerful enough where it no longer needs solid boosters on side. It's like core would be like, I got this, and solid booster only if you need to send something very heavy, for example 7-ton to geostationary orbit, then you will use that. So a lot of development happened just because of this project, and I'm just talking about few parts. There are many, many, many more. Even like how do you make seals that is super easy to make and low cost. A lot of other things like that. Now, this far is the good news. What I'm going to go after this is bad news. If you do not want to hear bad news or bitter news, you should tune out at this point in time. Click away the video. So if you are watching after this, it's on you. So what exactly is the problem? Well, problem is speed. SCE project, the furthest back I could find is 2009. This project was greenlit in 2009. That is 14 years ago. We should have full built rocket at this point in time, not, okay, we have just tested a power head. Full built rocket would have been like, yeah, we have flown at least 2 or 3 missions. So this took ludicrously long. Now, there's many what we call coping mechanism Indians have. One of them is like ISRO does not have money. That is partially true, partially false. For development and research, it has money. It's like, yeah, does it has the same funding as ISRO? Basically NASA? Hell no. But NASA also has a lot of high expenditure item like ISS. Look at the cost of ISS. It's the running cost of it. It's idiotically high. So practically speaking, ISRO is not in a position, oh, it does not get any money. It gets a lot of money. So it got around 1,798 crore rupees. Now, what does that translate to? That translates to 200 to 220 million dollars. That's a lot. Now you're like, wait a minute, that does not sound much. For corrupt organization, that's not much. But for small companies, that's a lot. Like how small? SpaceX kind of small. As in SpaceX started when Elon Musk got his money from basically this system, so to say. PayPal, I think, PayPal sale and all that jazz. He got around 100 million. He built whole SpaceX on that seed fund. So 200 million just to build the engine. Let that sink in. Build the goddamn engine. It's not like build the rocket. Rockets are already there. To launch pad, all that, nothing. Just the engine. So yeah, that's a really, really bitter thing. I genuinely, from bottom of my heart, hope these datas are wrong. Now, another aspect is, this was Elon Musk's true genius. Everything else Elon Musk did was clever, but this was his true genius, where it's like, whoa. The genius part was that he realized nobody, as in, be it ESA, be it ISRO, be it NASA, be it any Tom, Dick and Harry else, did anything other than Control C, Control V after Cold War ended. Once funding dried out, the Cold War funding, everybody stopped, basically pens down. Nobody was building anything new. So all the engines that you see right now that are either in construction or being deployed by all these big agencies, all of them have been planned, dreamed up, designed, or even sometimes almost pre-built to a point in that Cold War era, so to say. And Elon Musk's brilliance was like, hey, what if we use, instead of 1970s, 2000 years technology? What if that? Because we had a lot of industrial automation improvements. How about we use those puppies rather than 1970s technology? And that's why SpaceX was so successful. He figured it out. Like nobody was doing from scratch, like, blank paper, let's go. Nobody was doing that. He did that. Consequence, his engine sucked. Merlin 1 sucked a lot. But he kept polishing it because he was doing from scratch. He kept learning, kept improving, and voila. Now his engines are far more efficient in terms of manufacturing, in terms of getting things done, in terms of cost. Like it flat out bitch slaps everything else. Because of that, his light bulb moment is like, wait a minute, none of you did anything other than 1970. So we are taking the same 1970s design, RD8010. That's why it took me so long to figure out, like, how the heck you're driving a pump? Hydraulic, which we have let go so long ago. Like entirety of rocket industry realized, like I'm pretty sure if you have watched a lot of rocket failures, many times they will say hydraulic failure. How the heck that happens? This hydraulic system is one of those things that nobody wants to run on it. Like it's a big bulky system. You do not want to rely on it. You want to rely as minimal as possible. Like look at SpaceX, like they are removing so much hydraulics that their rocket built on the old design of 1970s, it will have hydraulics up its ass all the way. Now they're like, no, very few minimal hydraulics, so to say. So, and our speed of development is very slow. Now, why is that so? Do we have dumb people? No, it's slow because we are constraining ourselves with the design. SpaceX could literally iterate on its design because the design is theirs. We could not do that. Like there could be 10 geniuses in ISRO right now. They're like, bro, can I just start from scratch? Like I'll make a better engine. I guarantee you I'll make a better engine. I can make you a cheaper engine. I'll make you more safer engine. We have developed that much in technology. But it's like, no, we have to use this design. I'm like, why? I'm pretty sure the engineers working there, they will be more pissed than I am. And we cannot increase our speed even in future because this is the exact same thing we did with our PSLV rocket engine, that is Vikas engine. Now here's the deal. That sounds awesome. That's an Indian made indigenous engine. No, it's a Viking engine taken and just like modified and all that. That engine is so ancient in design, it actually has a water tank to keep it cool. Not even joking. It has water tank. Like you're like, wait a minute, that sounds old. Yeah, that's a V2 rocket. That's a V2 rocket era technology. That's why we can never grow out our wings because we are never starting from scratch. We are not learning to the base level or even freedom to ourselves. Hey, bro, we thought this design works. Yeet it. Let's redesign something simpler. It has so many manifolds because again, so many pipes, so many complexity. It's like, dude, it's like bonkers. And we can, it's like somehow we are scared of zero. It's like, hey, blank paper. We are like, no. That bothers me. It's like, why we are so scared of blank paper? We can develop every technology that we need to develop. We have some smart people, like seriously smart people. So it's like, why can't we do that? Like to give you a context, how far back we are talking about, 2009, this dude got elected that time, and the dude ran for 2 whole sessions, and then George Bush, I'm saying, basically, Donald Trump came. He ran for 1 session. Now we have another president. That's how long ago this was. This was the project that NASA was working on at that time. You must have known that space shuttle went poof. Okay. SLS was not ready. Okay. What was in between? In between there was Constellation. Constellation, the idea was take the SLS, basically space shuttle hardware, just use it, direct use it. Like this puppy, just use the booster itself. And they did testing, like they not only got it in launch pad, they did launch it and it worked amazingly well. But Obama poofed this project. It was too over budget. And then they were like, SLS was like, I will show you over budget. So that's why I specified, like, I really, from bottom of my heart, I hope this data are wrong because it's like 14 years, 1 engine, like just start from scratch. Like take all the learnings that we have gained from Rocket Labs, from SpaceX, all the learnings, they are available for free. Learn from it. Let go of 1970. So how does it contrast to other things? Well, reality is we are not learning from our mistakes in the past. For example, India has its own satellite system, navigation system, but it's a regional system. So it's Navik, so to say. Now, it had faulty atomic clocks. Now, be mindful, this was an issue even with European engines because same vendor was used for the basically European Galileo system and Indian Navik system. But that vendor messed up something bad. as in like multiple atomic clocks went poof in orbit. Even the backups, basically you have at least 2 or 3 atomic clock in basically navigation system, and all of them simultaneously poof, 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 done. So that created an issue where we are stranded. Now, because that vendor was not Indian and we are not developing that thing, we could not, fix it. So then we had to, okay, we're going to build our own. Here's the deal. What if we built our own from day one? Like, and we should have learned from this. We should have learned from it. It's like, no, we will try to build it from our own. If it fails, we'll learn more. If it succeeds, awesome. But no. Every time it's like, every time I try to look into ISRO's technology, it's like memorandum of understanding with Russia, memorandum of understanding with this, memorandum of understanding with that, memorandum of. So that's the whole point. And we are not learning from other companies that have done awesome work. For example, this puppy Merlin engine, like current variant looks good, but here's it's garbage engine. But here's why the heck it works if it's so bad? Because it's efficient in terms of manufacturing. They figured it out. The rocket engine does not need to be magic. It needs to be good enough. But if it is super easy to make, they're like, bro, oh yeah, you have awesome engine. Awesome. Yeah, keep making 2 or 3 of them. We'll make 20, 30 of them. That's the whole point. That's his genius. It's like, it's not, rocket engine does not need to be awesome. And all the learnings he gained from this, now he's putting in Raptor. Raptor no longer requires a third-party igniter. The igniter of this engine is this big. Not joking. It's this big miniature rocket. So it's one of those things we are not learning. And all of these companies started with chump change and they got bigger than ISRO very quickly. SpaceX is like, people are like, oh, SpaceX has money. It got that money from investor. Why did investor give the money? Because he showed that I have something interesting. Here's the deal. This puppy has achieved 100 landing. No other puppy has even one landing. This puppy has 100. On top of that, while I'm making this video, SpaceX crossed a milestone. They are consecutively safe orbital launches 200 times. 200 times. And the dude started at 100 million. So that's the whole point. Of course, he got money. Of course, he got support and all that. But because he showed that I'm doing something unique, I'm doing something awesome. That's why people gave him. And ISRO also has that benefit. ISRO is not tied to there was like, oh, I will not launch from someone else. No, ISRO is like, bro, if Bangladesh wants to send a geostationary satellite, we are like, bro, we got you. If OneWeb wants to sell satellites, we are like, bro, we got you. So ISRO can make a lot of money if it has awesome rockets. It's like money is not an issue. Neither the money that we got for development. So neither of them. And we are still stuck in ourselves in like patting ourselves in the back because we are comparing it to NASA. We are not comparing it to private players like this puppy. He built a tiny rocket engine. You're like, oh, it's a tiny rocket engine. Here's the deal. He learned so much from this. Now he's building a bigger engine. And I can guarantee you, this puppy will be responsible for building a bigger, better, more reliable, more efficient system. And this puppy will randomly be like, oh, now we have a big ass rocket that is reusable and cheaper and more efficient. And same with Firefly. Every time you build from scratch, from yourself, you get that competency. That competency allows you to turbo boost your speed every time you use it. So that's why ISRO is like only competing to either Pakistan. Yeah, we are awesome against Pakistan, but that's really not, that's like saying India has more economy than Sri Lanka. It's like, really? Like, really? That's what we're going to go with? So it's one of those things that we have to realize the market has become free for all. And these 3 players, again, there are many more. These 3 are my selection. There are many more coming. And once Blue Origin actually starts to reach orbit, yeah, we are talking some serious deep pocket doing some serious technological improvement. So that's the contrast. That's the part that hurts. It's like, let go of your fear of blank paper, a fear of failure. Because again, we are failing just because we are losing all our contracts, extra contracts as in. Of course, national payloads will be launched from this, but we are not growing simply because ISRO is like, what if we copied a rocket design? What if you built it? Like, we have enough smart people. We got this. That part is sorted. We are building CEOs for other companies. We got it. We got it. We solid. We good. So this was my presentation on basically ISRO's semi-cryogenic engine 200-ton class. Hopefully you have liked it, learned from it. In that case, please click the like button, share it amongst your friends. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike, press it twice to show me extra disappointment. Please leave a comment because I do try to reply to all of them. Subscribe, press the bell icon if you're free. And as always, thanks for watching.